Hi everyone, my name is Luis Jerónimo Miranda and I am going to present the next work, the synthesis and characterization of palladium carbon using the Leidenfrost effect and their performance as anode in an alcohol microfluidic fuel cell. In this work, palladium carbon are catalyses were synthesized using an conical aluminum Leidenfrost reactor. The effect of droplet volume of Leidenfrost temperature, palladium particle and crystal size at its dispersion on volcan carbon is reported. These catalyses were evaluated as an anode on a microfluidic fuel cell with the perspective of an application of the detection and quantification of ethanol in human blood. On the introduction section, we have the Leidenfrost effect is generated when a drop of liquid meets a surface higher than its boiling point, called the Leidenfrost temperature. In these conditions, a vapor layer is created and isolates the liquid front to the hot surface. The vapor fields reduce the heat transfer to the minimum, prolonging the life of the drop and generating vibrational movements that can be used for the formation and dispersion of nanoparticles of carbon materials. Due to these characteristics, the synthesis of a catalysis using the Leidenfrost effect is an emerging field in chemistry. In fact, today there are a few reports of a catalysis using the methodology in the literature. In this regard, it has been reported that the Leidenfrost temperature of a liquid is a function of the chemical composition and size of the droplet, as well as the geometry and roughness of the surface. This work presented the zinc and construction of a conical aluminum Leidenfrost reactor for the synthesis of palladium catalysis on volcan carbon. The evaluation of the palladium carbon catalysis as anode in a micro fuel cell were also investigated. In Figure 1, we have the synthesis system used in this project. The methodology that was used in this project consists of 5 important parts that are: number 1, determination of temperature with pure water. Number 2, the determination of temperature with water plus carbon. The catalysis synthesis, the catalyst characterization, and number 5, the fuel cell evaluation. The results of the project were as follows. In the table 1 shows the temperatures that we recorded at different temperature to determine the Leidenfrost temperature from the graph on the right side. In Figure 3, transmission electron microscopies images are shown for each of the syntheses, and where we can obtain the average particle diameter. In Figure 1, we have X-ray discretion images where they were compared with crystallographic charts to determine if there is presence of palladium and carbon. In Figure 1, we have XPS tests where the elemental composition of each of the catalysts was determined. In Figure 6 and 7 shows the results obtained from the fuel cell, where the potential is represented on the x-axis and the current densities on the y-axis. This helps you determine if the cell works better with or without alcohol. Like conclusion, we have by the conditioning the system, it was possible to obtain the minimum Leidenfrost temperature in the conical aluminum reactor for each volume of water drop and water carbon. Throughout the team tests carried on the catalysis, it was possible to observe the size of the nanoparticles and their dispersion on the volcan carbon. In this way, the synthesis conditions that produce smaller and better distributed palladium particles were identified, with potential application to produce electrical energy in a microfuel cells with ethanol in blood and urine.